Thank you. So thank you for having me here. So let's just get to it. I mean, no introductions. So I'm sure many of you heard at some point about property-based testing. It usually goes something like this. They say that you'll write one property and you get many hundreds of tests for free, not like just one measly unit test. And that sounds all very promising. And then someone will show you an example. For example, here we're checking the associativity of addition. Or, for example, our brand new reverse implementation is being tested thoroughly so it doesn't mess up anything. And then you're kind of left on your own to figure things out. So it's not that common to re-implement your own numbering system or do reverse again and again and again. And so despite my best wishes to apply this to my own code, I'm usually stuck with the question how to actually apply it to real code that I'm actually working on. And there are, of course, various talks that tackle these very issues, but I want to share a slightly different approach to this. And instead of giving you rules of how to approach property-based testing, we're going to look at a sort of a case study of a production bug, and how we managed to use property-based testing as a debug tool to figure out this bug. And we actually used, or in this case I used, I guess, actually used the pillars of property-based testing to define some simple properties, debug with using random data, and a very neat feature of property-based testing, we use shrinking to minimize the examples that reproduce the bug in a minimal way, which is easier to understand and fix. I just want to point out that I created those quotes before ChatGPT was published, and it wasn't that cliche. So it's like a retro GPT, it's plain GPT-3, so you can appreciate that. But there aren't that many quotes about property-based testing in the wild that are funny, so that's what you get instead. Okay, so first we need some background about the system we're going to actually inspect and debug. So I'll start by saying that this is inspired by a real bug that I actually had in the production system I'm working on. And I really did use property-based testing to try and figure it out. But the example code I'm going to show you is so heavily obfuscated that even people who are currently working on that system probably won't recognize any of it at all. So with this disclaimer out of the way, imagine that you're trying to make a new startup. And so the obvious way to maximize your chances of success is to maximize the number of buzzwords you can legitimately use on your website. So things like crypto and deep learning and the likes are all words that we want to use. And so with this in mind, we'll try to build our startup. But first, we need some deep insight to kickstart our own company. And the insight is that people don't like ads. I think that's almost universal. As people have more and more powerful mobile devices, lots of compute is being wasted on those devices idling. So the brilliant idea that we came up with is start selling people's mobile compute to the highest bidder. That sounds like a reasonable thing to do. Because we're going to support various diverse compute jobs, we'll be able to maximize the various buzzwords that we can actually use legitimately on our web page. And in exchange, our users won't get any ads, so everybody are happy. So here's a quick overview of the system we're going to be exploring. So this is a very high-level overview. And so, of course, we can't present anything without some buzzwords, so we have to put them there. So we have a bunch of job providers, each one sending us a stream of various jobs, and we have multiple kinds of jobs. So some deep learning and Bitcoin and protein folding. Those are small DNA things. Protein folding because we really want to give back to the world or something. And this all goes through our system. But because we're going to be running arbitrary jobs on our client devices, we take security very seriously. So we have this security manager, which after clearing only the secure jobs, sends them to a queue. It's all reactive. And then we send it off to our clients, which is kind of edge computing, so more buzzwords, and we can be happy. And the focus of this talk and the bug that we're going to explore is in the security subsystem. So here's a zoom in of the security subsystem. So it's one of the oldest pieces of code in the code base, so it's accumulated lots of kind of weirdness and craft that we have to maintain. The biggest weird part is the fact that the inputs are batched due to various performance and legacy reasons by provider, and you have like a batch of batches. So each provider sending us a batch, and we batch those, and we get a batch of batches as an input. It's a shame that we didn't know anything about streaming at the time, but what can you do? So next we go into the security ranker. This component is ranking those jobs by and giving them a security grade, and the ones that failed, that are completely safe, are being sent to the job queue. But those that failed the security ranking are going to a deeper security tracer, which is a proprietary component that goes deep into the job and tries to figure out whether it really is dangerous or can it be safe. And because it might be dangerous for the host machine, we're wrapping everything in a security sandbox. And the security sandbox is the most fiddly and annoying part of the system. And it requires careful management, which we'll see later on. Of course, we can't do anything without buzzwords, so we're not just ranking, we're using data science, and security tracer is obviously powered by AI, maybe ChatGPT directly. Okay. So now that you're kind of familiar with the high-level overview of the system, we can actually dive into our production bug. Okay, so the bug, one day we get a bug report. It looks like the following. Since recently updating from Java 6 to Java 7, about time, seem to be living in the past. I heard there's like Java 21 now or something, I don't know. We started getting occasional exceptions about the security sandbox getting corrupt. And that's it, no other clues. That's the bug report. So we scratch our head thinking about this, and obviously the first line of defense is some print line debugging. That's what most developers use most of the time. So we look at the code that originates the exception, that does the signature. We're getting a batch of batches here, a list of batches, and we do some side effects. So we can start by printing out the inputs that trigger the exception. So here's an example input that trigger an exception. We can take this directly from the production logs, put it into a small unit test. In this case, we create a unit test that takes this input, places it here, then sends it to the security subsystem, and asserts that the sandbox is actually corrupt. So we're trying to reproduce the bug as a unit test, and we run it, and it failed. So no such luck. So although the input was corrupting our production system, it doesn't reproduce in the test. And if you think about it some more, you probably reach the conclusion that it's probably a stateful bug. So the state of the sandbox is somehow changing over time, and that's why we have something going wrong, not from a single input, but maybe from a chain of inputs. So at this point, we can only pray that it's not a multi-threading issue, because no one wants to debug multi-threading issues. But luckily, the security manager is very old and very, very sequential. So we can hope that the bug is also sequential. And so let's try to reproduce the steps by taking a sequence of inputs. So here's a sequence, a very long sequence of inputs we took from the production logs. So it's long, but at the end, production was crashing. And we can rewrite our test. It's now similar to the previous test, but now we have a list of batches. So we have multiple inputs, all of them fed together into the system, and we should get the system at the end of this sequence. We should be corrupt, like in production. Run it, and failure again. So it doesn't reproduce, and but if we think about it again some more, then if the problem is stateful, who knows where the sequence should start? So, for example, we just took a random bit from the sequence, but maybe the whole sequence started for like days ago, and the log might be long, and it might get very tedious to actually figure out which exact sequence was triggering the problem, and And so it's part of the nature of stateful bugs, what they call spooky action at a distance, where the cause and effect may be very separated from one another over time. But why should we specifically randomly pick various outputs? Why not generate all of them and test it automatically? And that kind of leads us to property-based testing, naturally. Okay, so unit testing and print line debugging just failed us. So we're now ready to tackle this problem with the actual property-based testing. Probably the reason why you came here, I hope, maybe. So finally, we're getting to write an actual property-based test. So seeing how magical property-based testing is supposed to be, it should be like no time to just generate some inputs and get the bug reproduced locally and be done with it. So we define our own property in this case. So it's very, very similar to the unit test we started with, but we replace the specific input with a for all clause, which expects the input to be generated randomly for us. So the property that we're asserting is that no matter what input we get, the sandbox should never be corrupted. So that's the property that the system should have, and we just defined our very first property for a real production system. It's a simple one, but it's a real one. And so hopefully we can drive our system into an error and see the corruption happening there, and it's green. But it's not the right kind of green, unfortunately. So it says that our system doesn't have any problem. So this property now, apparently according to this test, our system has this property of never being corrupt. And we know that that's not the case. We know there is an actual real production issue. So maybe property-based testing is not that magical after all, but we won't give up. So first order of business is the fact that we see the test is running fairly quickly. And one of the things you should probably figure out about your property-based testing library are the defaults that are being used, and usually they're quite small, and we're possibly running too few samples to actually be able to find the bug randomly. So we can make it a bit larger. In this case, we're going to sample at least 2,000 inputs into our system, and we're going to run it again. And it's still green. But at least on the bright side, it is running longer, so we are testing our system more thoroughly. But at this point, we might just give up on property-based testing and move on. But it's not this kind of talk, because that will be very disappointing. So let's start to think about it some more. So this is the component we're testing with all of its dependencies. And so it would make sense that the bug we're searching for is some bad interaction between the various subcomponents that this security manager is using. And so the more components you have, the more cross interactions you might have between the various components, and the larger the state space of possible errors and possible interaction will become. So it's quite possible that, given that we have so many components here, that the state space is so large that it's very hard to pinpoint the specific bug within this large state space. So our goal here is to strike a certain balance where we can minimize the state space to something that we can actually explore effectively and actually find the bug, but not minimize it too much so that the bug disappears completely. And we're going to achieve it by using some mocking. So we're going to make partial mocks of the various components here. In this sense, we're going to make small models of the actual production system with various assumptions that would allow us to be realistic enough to reproduce the bug, but still simpler than the actual system, so that the state space becomes smaller than the original state space of the system. So what's important here is not to mock too much, because if you make your mocks completely trivial, obviously the bug won't appear here. So this is where things are becoming more speculative. So it's kind of an art rather than a real science. We have to guess which things we should mock out. So we'll start from the end. So the job queue doesn't really interact with the security sandbox, so we can cross that out. Security tracer is a complicated third-party component which would be very complicated to mock, but we can just assume that it's working at the moment, because we just really can't tackle it. Then there's the sandbox optimizer. So the purpose of the sandbox optimizer is to kind of reduce the number of times we open and close the sandbox, because it's an expensive procedure. So it kind of computes how many where and when to actually open and close the sandbox. But it's essentially a complicated pure function. So pure functions are usually good candidates for property-based testing themselves. But unless we reproduce the logic of this function inside the test, our mock is either going to be too trivial or going to introduce its own bugs. So it's not that good a candidate for mocking. And so because we're left with only a single component, it's the security ranker, the last one that's left here. So the security ranker is actually a very good candidate for mocking, because it's basically a black box that does some side effects and then just produces a ranking. So we can come up with kind of a nice model of how this component should work, and then model it as a mock. And we can follow the types of the actual signature here to figure out what would be a nicely behaved mock that might help us reproduce the bug in a more convenient way. So we start by following the types. It's always a good idea to follow the types. So we see that we have a somewhat complex output. So we're doing some side effects, but they cannot fail. So it's an unexceptional I/O, which produces a ranked batch. But the ranked batch itself has some nesting in it, which has three major behaviors. One, that the output can be empty. The option can be completely empty. The other is that the list inside can be empty as well. And the last is that we actually have some security ranking going on here, and that will be the third behavior. And we can model this as an enum that actually models those behaviors. So we can say that one of the three behaviors I just described, where for the last behavior, where we actually have a list, we'll just assign some random ranking, which is pretty much what's going on from our point of view as the clients of this code, and hope that this is enough to reproduce the bug. So hopefully this model is rich enough to reproduce the bug, but it does have a smaller state space such that we will actually manage to generate random inputs that hit the bug while running the test. Okay, so here's the new property. It's very similar to the previous one, but instead of just generating job batches, for each job batch, we're generating a behavior as well, and we're going to feed this behavior to our mock, and the mock will do the appropriate thing for this behavior that we just generated. And so again, we submit all of the batches and check that the sandbox is not corrupt, and failed again. So that green is not the right green, right? It means that the property still holds for a system, despite all the mocking, despite having thought about it, followed the types, everything. And we really, really tried, and it seems that property-based testing is really not that great, I guess. So that's our cue to kind of step back and kind of regroup and figure out what went wrong. So property-based testing is actually quite a rich topic. If you Google it, you'll see various articles and methodology, and it's not something trivial to just plug and play and hope for the best. So there's lots of nuance and fine details. And we're hoping to just kind of magically run some random inputs and just do it, but maybe we should invest some more effort into the actual process of property-based testing. So successful property-based testing hinges on the ability to generate good data. What good means is very, very context dependent, but for our purposes, we needed to strike a certain balance where if the data is not random enough, we won't hit our bug because we don't get enough randomness. But if the data is too random, we might be just scattered around the whole state space, and we just won't have much chance of hitting the bug accidentally. So we need to create a state space that's large enough to cover our bug, but not too large so that we scatter around it and can't actually pinpoint that bug. But in the case of known bugs, where we actually know that we're searching for some existing problem, we can try to minimize the state space by constraining the inputs to be something that's realistic. Realistic, again, is context dependent, but guided by production logs, we can try to minimize the state space by minimizing the inputs to something that's not completely random, hopefully, but while still reproducing the actual bug. So the conclusion from this is that you need to inspect your generators to take a look what they're actually generating and make sense of whether it's appropriate for the system you're trying to test. And so we can do just that. So for example, here is the distribution of behaviors. So it's just 30% on 1/3 for each behavior, and there's no reason to think that we need something else. Same goes for the types of jobs that we're generating. So again, uniform distribution. And again, no reason to think that we should skew that somewhere. But then we have the providers that we're generating. And that's just a mess. We just have many random strings with very small probability. That's not realistic at all. And we can fix this by making a generator that's much simpler, smaller input. And realistically speaking, we don't have that many providers in our actual system. We have like 5, 4, 6, whatever. But it's not going to be thousands of providers. And so by constraining our generator this way, we're going to reduce the state space that we're crawling around, but hopefully in a way that still doesn't prevent the bug from showing. So this should be a step in the right direction. And now the distribution is what you might expect. So with this diversion out of the way, let's run the actual property. And finally, that's what we wanted. We were looking for the red color. So we managed to hit the bug. with an actional input. It got shrunk away into something very, very minimal, so so the library really tried to shrink it. And we can see that the input is just three batches with no jobs in them, and only two different behaviors, empty list and empty option. It's a very minimal, it's such a minimal example that we can actually try and just print line debug again on this small input and just trace the execution and see what went wrong, because with such a minimal input, that's actually manageable. So back to print line debugging, we're going to add some printing into our flow. So this is the log that we're going to get from running the failed example, and presumably something here is wrong. But to make it clear what actually went wrong, so here's an example of another trace of something that was successful. So this is a successful trace, this is a failed one, and so let's try to see how a successful trace should behave. So one thing that we can notice here is that for each provider inside a batch, we open it at some point, but then we must close it somewhere within the same batch. And that's the purpose of the sandbox optimizer. What it does, it tries to minimize the number of times we open and close the same provider, because it's a costly operation. And so when it sees a single batch, it analyzes it and finds what's the latest point it can close the provider. And so this is actually a nice property that you can formulate for the systems. Like every optimizer must close every provider that ever opened. But in this case, if we look at the failed trace, we see that we opened the sandbox for P3 and then we never closed it. And then when we open it again, that's when we get the corruption. So it's one of the rules of the API of the sandbox that we can't open the same provider twice without closing it in between. And it also explains why the error was so non-local, because we might open and forget to close the one provider one day, and then some other day we'll actually get another job from the same provider, and then we'll fail with the corruption. And that might take time again. So that's why we get stateful non-local spooky action at a distance. But why didn't we close the sandbox in the first place? So at this point, I don't have any choice but to actually show you real code from the system, supposedly. The code is terrible. I usually avoid showing code like this in presentations. I don't like ugly code on my slides, but this is really part of the point. So obfuscated bad code is something that's more prone to bugs than nice, clean, and lovely code. So you'll see now something terrible, and don't flinch. Just bear with me. So it is terrible code. Way too many lines for a slide. By the way, Scalar 3 is very lovely for slides. You can really optimize the vertical space here. So the code is terrible because it's full of units and discarded results and even a callback, something that we usually don't see much in the Scalar world. It's as if descriptive types and streaming wasn't a thing. But the structure is pretty much matches the diagram we saw on one of the first slides. So given a list of batches, what we do here is we predict the security level of each batch here, and then the optimizer figures out when and where to close each provider. So it analyzes the batch and then adds the pre and post conditions for each provider. Then we go over the ranked batches, open up the sandbox, that's the acquire release here, and then we do the security trace, which rejects any unsafe jobs. And if it succeeded, we submit success to the queue at the end. So what went wrong? So it seems like we should be safely acquiring and releasing the sandbox. So this line here is supposed to guarantee that we were actually always calling the post condition after finishing the execution. So why did we miss the closing of the sandbox? So in the logs, we saw that in the output from the property test, we saw that the relevant behaviors are empty list and empty option. So empty list doesn't seem to be relevant because empty lists go here and it's inside the acquire release block, so it shouldn't interfere with closing the sandbox. But where did the option go? So if we have an empty option, what piece of code does it affect? And it's a bit difficult to see within all the various for each here calls here, but it happens here. So we only perform the required side effect, like closing the sandbox, if that option is present. So if and this is sometimes a problem with very polymorphic functions when mixed with the unit type. It's very easy to miss something going on that's a side effect that doesn't happen because a unit is always discarded and no one cares about units. And so that's something you should probably avoid. But now we can see that And within all those lists and batching, it's quite easy to miss. So what happens in the problematic scenario is that we're skipping the post condition of the job because the option was empty. So let's just trace through the code. So what happens here is the optimizer sees that P3 is used twice, so it opens up the sandbox here and schedules to close the sandbox after this is completed. But here we get empty options, so we never call the post condition because we skip the side effect when the option is empty. And then next time when we get P3 again, we open the sandbox, and that's the corruption. So this is a better interaction between various different components. It's something that's very tricky to debug because when you do it separately, each component seems to look fine. But in this case, we had a very naive optimization strategy that interacted poorly with the behavior of the actual ranker. And with such obfuscated code, which you should obviously avoid, it's very easy to miss that some side effects are not present in the code. So how do we fix this? So we might first wonder where that option came from. So this is the function that does the prediction. It's kind of a leftover of some legacy API, so it does some wrapping and stuff to interact with newer code. So we're wrapping everything with a try and then discarding the exception with the option. That's never a good idea. You should never discard the exceptions silently and without any trace. But in this case, because we had an unexceptional I/O, we might as well just take this exception and integrate it into our I/O value and just wrap it there. And then the new signature will become something that can have an exception, and the option will be gone. So we no longer have an option of a list of ranked jobs. And now the property passes for real. So this is a real green. That's the right color for now. The property holds within the system that we just fixed. So no more option here, and we will no longer skip closing the sandbox in any scenario here. So the non-corruption property that we defined for our code seems to hold, but there are still some issues left. So we only verified the mock system. So we had a model of how the system should work. We never managed to reproduce the bug on the actual system. We have no idea why the none occur in the why did the none value occur in the first place, and what does the Java 6.7 upgrade has to do anything with it at all. So we can take a look at the actual ranking. We see the code here. So the obvious suspect is that the assigned security rating is doing something wrong. But as a mere security team, we won't be touching data science stuff. So we'll just leave it as is. But at least now we no longer swallow exceptions. And if the bug reproduces in production, at least we'll have a real stack trace to take a look at and maybe debug it further. But for now, at least the sandbox should be safe. OK, so we deploy our fix to production, hoping for the best. And it works. No, we no longer get any security sandboxes corrupt exceptions, which is great. But then we started getting a new exception, a legal argument exception instead, with comparison method violates its general contract, exclamation point, no less. So since when Java is so excited about exceptions, I have no idea. But at least now we have an exception, so we can see where it throws, and it throws on the sorting part, which seems to be the most benign part of the code here, no less. But since when sorting throws anything, for me at least was a real surprise, not just for this presentation, but in real life as well. But now we're back to our old hammer of using printline debugging, and we can just printline and see what output caused it to fail. And this is the output. It's a bit long, so it kind of looks random and hard to learn something from it. But now we know about property-based testing, so we can try to just formulate a property and shrink this output into something that we can actually manage and debug like we did in the last section. So here's the new property. It's a very basic requirement. We say that for all lists of ranked jobs, we should never throw on sorting. So we can generate some outputs, and here's the output from the property. And there's no shrinking here, supposedly, but it tried to shrink something. It did 700 attempts of shrinking, but still, we get this. And suspiciously, all the lists fails on are of length 32. It probably can't be a coincidence, but I have no idea. But we no longer have to actually rely on property-based testing anymore. We have a stack trace. We can just dig into the actual problem in the actual code. So here's the relevant piece of code. And it throws right here. So I'm not as fluent in Java as I used to be. thankfully, I think, maybe. But that's some seriously impenetrable code. I have no idea what gallop means, and there are like plenty of lines of code doing this, so it just goes on and on and on. So I don't think just staring at it probably won't lead me to a solution to the problem. I won't be able to figure out this code. So the stack trace wasn't that helpful, but it is the JDK. Unpleasant as it may be, we can just read the documentation. And we can do that. Apparently, sort is allowed to throw when the comparable that was passed to it violates its contract. And it might be an interesting discussion to figure out whether throwing is the right decision here. But nonetheless, we can move the documentation of comparator. And here's the contract that we're supposedly violating. So surprising to see it in Java, but this is one of the properties that the compare function must obey. So in this case, something to do with flipping arguments and sign inversion. And Java is literally telling us which property we're supposed to write to test our code, and there are a couple more. But we can just take this documentation, translate it into actual properties, run it, and see where we managed to fail. So here's the translation. So that's the first property. It's a fairly straightforward, taking from the Java doc and translate it into actual code. And we can, with a bit of trickery, can figure out the other properties as well. It's not that complicated. And now we can run this, and lovely. We have a failure that actually pinpoints the actual problem with our comparator, or ordering in this case. And we get a very minimal reproduction of this error, and we can see that if we run it multiple times, that it always fails on folding proteins, and always with the same security ranking. And now we can finally pinpoint the bug. So that's the ordering instance that we're failing on, and we actually have a nice comment telling us what it should be doing. So we order by security ranking, but as a tiebreaker, we prefer the protein faulting jobs because we really want to give back to the world. It's in our DNA, and also a business requirement. And so I'll go quickly because I'm pretty much done. So we start by ordering by security rating, and if it's equal, as a tiebreaker, we prefer folding proteins. So if the first argument is folding proteins, that wins. If the second argument is folding proteins, that wins as well. And we can see, so can anyone see the bug here? What's the issue with this ordering instance? Okay, so if we have both arguments to be fold proteins, we get the first case and get a 1. But if we flip now the arguments, we still get 1 because fold proteins is still the first argument. And the solution, the fix is very, very simple. Just add one line saying that if both of them are fold proteins, return 0. The flip sign of 0 is still 0. And we can run our properties again. And finally, that fully resolves the original bug. The exception won't be thrown anymore. And I'll just quickly recap the full bug so that you get the full picture, and I'll be done. So we started with a very buggy ordering instance that sometimes triggers an exceptional sort, but only on relatively long lists of at least 32, because the team sort, the sorting algorithm used by Java, uses chunks of 32. So that explains why the minimum examples were 32. The exception throwing behavior is something new in Java 7. That's why the update triggered new exceptions. Exceptions, we did some interaction with integration with legacy code, with solid exception, never good exceptions, never a good idea. Unit-driven and imperative code is also a bad idea. Confusing multi-level batching and avoiding streaming instead, also obfuscating the code. Naive resource optimization kind of swallowed inside the whole thing. And the result is this long-winded bug, which required very specific and quite long inputs. That's why it was so difficult to debug. And to conclude, we use property-based testing for an actual debugging of a real scenario, so in a real system. It's not magical. We have to work for it. We have to actually think about the problem and do something. But it's not just math. We can use it in something more real. And sometimes Java also produces mathy kind of things, and we got to use property-based testing in a more classical setting. And just like a final note, the data science team analyzed some data, and apparently the broken sorting is more profitable for our company. And luckily, Java got our back. We can just revert to the old sorting algorithm just with a single flag. We have avoided the whole thing to begin with. And I'm out of time, so this is the full code with the slides, and you can actually run the properties and do everything. And thank you.
Thank you, Daniel.